Click the bell icon to get latest videos from Ekeeda.
Hello friends, in the previous lecture we have got to know about what is valence bond theory, and this shows us that how the bond forms between the two different atoms. And based on that, we have also discussed about the which of the orbitals are basically responsible so as to form the overlapping, and that is how a bond is being formed between the two atoms. But now we are going to talk about hybridization. So what is hybridization and how it has been evolved? And by evolving, how it has discussed about the limitation of the valence bond theory that we have did in our previous lecture. So let us talk about this thing. And we are going to discuss about in this lecture that because of the failure of the VBT, that is valence bond theory, the hybridization concept has been evolved, and this suits very well. So let us talk about it. So the first thing that is I'm going to talk about is I'm going to discuss about here the failure of valence bond theory also, and based on that we are going to discuss about what is hybridization, and that hybridization is very important for us to understand, and it gives us a very deep detail not only the bond but also the bond angle or the property of that kind of molecule which is undergoing hybridization, and everything that we are going to discuss in this lecture. So talking about the first one, that is how the VBT has been failed. So talking about the VBT, that is, it was a concept which was related to that a bond is being formed because of the unpaired electrons that is present in its orbital. That is, for example, like hydrogen. Suppose if hydrogen has one electron in its outermost orbital, and it is combined with that of the fluorine. Fluorine has also one electron in its outermost orbital. That is p orbital. So now, because of which they can combine with each other, and that was the basically the feature of the valence bond theory, and that is how the H and F bond is being formed. And so on, we could see that because of the number of unpaired electrons that are present, only that much amount of the bond will be formed by that particular atom. And this is what we have discussed in our earlier lecture also. But the failure comes here. If I'm talking about the molecule like BeCl2, so in this case, as I could see that beryllium is the one which is basically the central atom, and the electronic configuration of beryllium can be written as Be is equals to 4. So that could be written as basically 1s2, 2s2. But talking about the atomic orbital, so here there is 2 electrons, and the both are paired. So even though being paired, how can it form according to VBT BeCl2? Obviously, because chlorine is the one that we know that it consists of unpaired electron. Let me tell it again. That is, chlorine is the one which is having an electronic configuration of, we could write it in this way, that is 1s2, 2s2, 2p6, 3s2, 3p5. So if I draw the atomic orbital in this way, in which the p subshell consists of 3 atomic orbitals. So this is the first, second, third, fourth, fifth electron. And meanwhile, if you observe here, there is only one orbital is being present, which is having an unpaired electron, and that would be obviously that would be responsible for us to form a bond with that of Be, that is beryllium. But B doesn't have any kind of unpaired electron. So how can the bond will form? So this was been explained by hybridization. So that is what we are going to talk about. And talking about the another molecule like CH4. So carbon, which has an, I would write it over here and just to give you a glimpse about it, that why we are studying hybridization in a very deep way. So talking about CH4. So hydrogen is what we know that it consists of one unpaired electron. And talking about the carbon, carbon is the one which is having a electronic configuration of 1s2, 2s2, 2p2. Okay, so talking about the outermost orbital, so that is p or p subshell if I am talking about. So it consists of basically px orbital, py orbital, and pz orbital. So talking about the electrons that are present at px and py, suppose. And this has been completely filled. That is, this s orbital has been completely filled. So it has only 2 unpaired electrons, but according to VBT, that is valence bond theory, only 2 valency of the carbon should be observed, or the only 2 bonds the carbon will be formed according to VBT. But is it? No. So that is what we are going to explain in hybridization. And talking about the bond angle also. The bond angle, for example, in NH3, if I am talking about NH3, so the expected bond angle that we would see for NH3 is basically it should be forming in this way. That is, again, we could say that the nitrogen is having 3 unpaired electrons, that is px, py, pz, and obviously they will form the bond with the only uni electron that has been present in the hydrogen outermost shell. or we could say like its orbital. So obviously we would see that there should be a bond angle of 90 degree because they are forming a bond because of the valence bond theory. But is it 109 degree that is the bond angle between them? No, there are certain uh, bond angle that depends on the structure also, that depends on the molecule also, and that depends on the hybridization also. So that is what we are going to talk about in this lecture, and how the bond has been a bond angle or the number of bond that has been that will be changed because of the hybridization. Let us talk about that too. So let us talk about hybridization. So what is hybridization and how the hybridization is being formed? So let's talk about that. So first of all, let us understand the definition of it. And according to the definition of it, it says that it is the process of mixing and recasting of atomic orbitals of the same atom with slightly different energy to form equal number of new orbitals with equivalent energy and maximum symmetry as well as definite orientation in space. This is what the hybridization is. So therefore, it is a process of mixing of or recasting of the atomic orbitals of the same element or the same atom. And obviously, it will have various orbitals like s orbital, p, d, and it will depend on that. So now, this atomic orbitals, they will form or they will be, that is, recasting themselves in such a way that they will form a new atomic orbitals that would be having an equivalent energy, that will have a maximum symmetry, and yes, they will have a definite orientation in space. And this definite orientation in space is responsible for giving the bond angle of the between the two covalent bond. So that is what we are going to talk about in this lecture. And let me give you a short glimpse of it. And because there are various examples also based on the hybridization that we are going to talk in the next lecture and separately. And let us talk it with the help of a few examples that I am going to talk about. That is, the hybridization takes place in the following steps, and that following steps are being very much important for us to understand it, because it will give an idea that how the bond has a valency which is very unexpected. So, like that of BeCl2, that was unexpected. We didn't expect it that according to the VBT that it will form two bonds, but actually it forms two bonds with that of the chlorine, two different chlorine atoms. So there are the certain steps that we have to that is follow, and those are: the first step is formation of an excited state. An atom which has suppose an unpaired electron which is not fulfilling the we could say like the valency of that particular atom when it has been formed, when that particular atom has been formed with different atoms so as to form a molecule. So in that case, basically the excitation state should be done, and what is that I will talk about later also. But and the next thing, that is mixing and recasting of atomic orbitals. Obviously there will be mixing and recast, that is what we have discussed in the hybridization definition. And the next is orientation of the hybrid orbitals. Obviously, it will be responsible for giving the bond angles, energy of the orbitals. Even that is very much important, because only the thing is that the two different atomic orbitals or the hybrid orbitals that I am talking about, so they will mix with each other in such a way that the bond energy should. In VBD also, we have got to know that they should have basically the same energy level, and that is what the fourth point is. And the last point, that is essential condition of hybridization. So there are a few conditions that we are going to talk about in this lecture only. So let us discuss about the first step. So we are discussing about the steps that are being involved, that is in the formation of a hybridization. But talking about the first one, that is the most important one, that is the formation of an excited state. What is excited state and how can we form this one? It is very much easy, because in the previous one only, that is during taking an example of BeCl2, we have got to know that the beryllium, according to the valency, it has basically two valence electrons, and both the electrons are being paired. So therefore, according to the VBT, it won't be able to form the bond between Cl or the chlorine atom. But in the actual practice, it has been found that there is bond between Be and Cl2. So how does this form? This is formed because of the following thing that I am going to explain you. So talking about the beryllium one, so beryllium is the one which has having an electronic configuration, or we could write it as in this way, that is 1s2, 2s2. So if I am representing the that is the atomic orbital, so therefore it could be written as in this way. Means I'm talking about S substance, so S has only one orbital, and talking about the next one, that is the electrons that are present in the valence shell, and that is basically two electrons. So therefore, I would write it here one. This is two. So this will not be able to form the bond with that of the chlorine atom. So therefore, what I have to do is I have to follow the valence bond theory. Yes, I have to make the orbital of this one in such a way that this each orbital consists of only one electron, and that would be able to form at least one bond with that of the Cl atom. So similarly, the one electron that has been left out, again it will form basically an atomic, or it will be occupy its space in atomic orbital, and now that would be also able to form the bond with the other one. So let me give you an example that what I'm talking about. So this that is electronic configuration that can be written as 1s2 2s2 can also be written as 1s2 2s2 2p0. And here what we are going to do is, here also we are mentioning the atomic orbital. Now in this case we see there will be no electrons that are being left in the p orbital, because the p orbital is very vacant, empty. So now this state that we have made the electronic configuration, so this is known as basically the ground state, or basically the normal state. So what if we have provided energy? Because even electrons can shift from one orbital to other orbital by giving some energy. Suppose if we are giving some energy to this atom, so obviously the electron will be able to, that is, jump from one orbital to another orbital. So this shifting of electron takes place with the help of the energy that we are providing to it. So in this case, since we are providing the energy, an electron will be moving from one orbital to another orbital, or you could say in this manner, that is from one subshell to another subshell. So obviously energy is being needed. So if we provide that particular energy, so electron will be jumping from lower to higher if we are providing energy. And the opposite, suppose if electron is jumping from upper to lower shell or subshell, then electron during that process will able to remove the energy. But that is not the concept that we are going to talk about here. We are going to excite it. We are giving the energy to it. So in this case, after giving the energy, and that basically we are giving the energy that makes the electron to be excited, and hence the name is excited state. So therefore the excited state will be where I could find this is the one that will be not involved in the bond formation, because it is very much near to that of the nucleus. But this too, where we can be able to form the bond with that of the chlorine atom. So here only I am making this as 2s orbital, I am representing it, and here as 2p orbital. And this is the orbital that I am representing for s, and this is for p. So after providing some kind of energy to this ground state, obviously the one electron can be shifted to the other one, and obviously this one electron will be moved in such a way that it will transfer to that of p orbital. But meanwhile, one electron, it will be left out in the s orbital only. So now as you could see that the electronic configuration, as you could see over here, is basically it consists of the s orbital consists of one electron, while that of the p orbital that consists of basically also one electron. And yes, now you can say that the chlorine atom can occupy in this space. So now this is how the excitation is very much important for us to shift the electrons so as to form a respective number of bonds or the respective number of valencies. So this is it, but it is not the ultimate thing, because as we know that this 2s and 2p orbitals are of different that is orbital, and that's the reason that they will have different energy, and they will have different energy, but meanwhile we can arrange in such a manner that they will have the same energy. So the energy difference between these two is there, but it's quite we could say that it's very much less, but we don't want less, we need negligible. Means we need the both the orbitals should have the same energy, and that is what we are going to do. That is, we are going to do the second step, and that is mixing and recasting of atomic orbital. So this is very important that we are going to discuss here now. So as the previous one, or as in the first step that we have discussed, that is we have excited these two electrons. So one of the electron, and this is how we have formed the orbitals. So what we are doing in the second step is we are going to mix these two orbitals that we have that is formed because of the energy that we have provided to it. And now they both will mix with each other and they will recast with each other. So in such a manner that I am going to talk about. That is the electrons that are being occupied in 2s orbital and the 2p orbital, it consists of unpaired electrons, that is one electron in 2s and one electron in 2p. So now they will arrange, they will mix with each other so as to form the same number of that is, we could say, the respective hybrid orbitals. So what is that? Hybrid atomic orbital. So what is I'm talking about is whenever the 2s orbital, I'm just discussing in here only, that is 2s1 suppose, and this is 2p1. So it consists of basically one electron, and it consists of also basically you could say like one electron. But during mixing, when 2s is combining with that of the 2p, they will form the orbitals that will have the same energy, and that is how we could say that the two atomic orbitals, they will mix with each other so as to form their respective atomic orbitals, and that atomic orbitals will be known as hybrid orbitals. And after mixing, so I'm just making a point over here, that is after mixing I'll get actually two hybrid orbitals, and those are this one, in which basically one electron will be of the 2s and one electron will be of that is 2p. So we can't say exactly that what it is of which it is electron, because they have now been mixed, and that is the reason that one of the orbital, that is what I'm talking about, it will be called as sp hybrid orbital, and here also it will be called as sp hybrid orbital. So the both of them are sp hybrid orbitals, and talking about the next thing, because they are belonging to the second chain, and that's the reason that 2sp orbital and 2sp hybrid orbital. So these are the two things, and now it will be very much responsible for us to form out so as to occupy two chlorine atoms. One of the chlorine atom will be occupying its electron over here, and another chlorine atom will occupy the space over here. And this is how the mixing and recasting of atomic orbital is taking place, and which is very important. And now talking about the next one that I'm talking about, that is let us talk about orientation. But before understanding orientation, let me give you a short idea. That is, in this case, basically the mixing has occurred because the two energy levels are almost the same. So if I'm talking about whether the mixing is possible between 2p and 3s, it is possible, but not firmly like that of the mixing that it has happened between the 2s orbital and 2p orbital, because they are belonging to the same, we could say, same energy level almost, and that's the reason that they have mixed with each other. And so that was the main point that I was talking about, but we'll discuss about it in more detail in our future lecture also. So now let us move on to the third point that I am going to explain you. So now let us start about the orientation of hybrid orbitals. And what is actually orientation? Because as we have discussed about in the second point, that is the mixing of orbitals takes place. But these two electrons that has been formed now here, because in different atomic orbitals, or we could call it as hybrid atomic orbitals. So the electrons are present in there, but mostly we could say that even the electrons are present, they can repel each other. So orientation plays a very vital role. That is, this is basically the distribution of the electrons that are being present in the respective atomic orbitals in such a way that there should be no repulsion or no kind of interaction that could create the disturbance in the geometry. So they will spread in such a way, or when we are talking about the orientation, that is, it is nothing but the distribution of the atomic orbitals in the space, and that is how it happens without any kind of repulsion or without any kind of distortion in the geometry or something, and it forms almost a stable structure, and it gives us the stable structure along with that of a bond angle, and that bond angle also plays a very important role, just like that of in the example that we have discussed earlier, that is NH3 don't have a bond angle of 90 degree. It will basically, it is more, because obviously the electrons that are been around it, like lone pair of electrons that have been present on the nitrogen, obviously this will create a repulsion. So therefore, without creating a repulsion, they will arrange themselves in such a way that is the repulsion between the electrons will be reduced, and that is what orientation plays a very vital role. And this is what I am going to talk about. So talking about this one, that is this example that we have discussed, that is BeCl2. So this is how we have got the atomic orbitals as 2sp hybrid orbitals. And so the structure of the 2sp hybrid orbitals, there are various structures like that of sp3 hybrid orbitals, sp2 hybrid orbitals, sp hybrid orbitals. But now for a while we are discussing about the sp hybrid orbital. So for that is beryllium, that is the hybrid orbitals that are being like this one. So this is formed. This orbital is being formed because of the 2s orbital as well as the 2p orbital. They have mixed with each other, and that's the reason that they have formed a new kind of orbital. Because s is the one which has a spherical shape, while that of the p which has a double shape. So now they will combine with each other in such a way that they have formed a new kind of orbital, hybrid orbital, and that is how we could see that the electrons can also be present in this case, and that is what I am talking about. So suppose this is the one which has an electron over here. Suppose two electrons like beryllium, and now it will combine with that of the chlorine atom, and chlorine atom is the one which has only one And chlorine atom is the one which is having one electron in its outermost shell, or we could say outermost shell in the sense the valency of it is 1. So therefore, the pz orbital, it consists of only one electron, and that is how the bond will form in such a way, so that this is the electron of chlorine, and while this is also the electron of fluorine that I want to discuss about. And now they are basically forming a bond like this way. But talking about the bond orientation is nothing but the distribution of the atomic orbital in space, so that they would have no repulsion. Obviously, as you can see, that they are opposite to each other, and that is how they will have very much less repulsion, and that makes the bond angle, that is 180. So this orientation also plays a very important role, and that is what I was talking about. And let us move on to the next one, that is the energy. So this is the next point that I'm going to talk about, that is the energy of the orbitals. Whenever that is a hybridization takes place for the same atom, and it forms a hybrid orbitals. So all the energy of the orbitals, of the hybrid orbitals that has been created, will have the same energy, or we could call it as degenerate orbitals. The reason behind that is because if you combine that of 2s orbital with that of the 2p orbital of beryllium that we have taken in the example in this case, they will have a small difference between them, but they are not exactly the same. But after mixing, they will form the same, uh, orbitals, or we could call it as hybrid orbitals, but that hybrid orbitals will have the same energy. So this hybrid orbital, as you could see over here in this region and this region, the both the one which will have the same energy, and that is basically the main reason why the orientation takes place. Because obviously we could see that suppose if one of it would have more we could say electron density, so obviously it would change the geometry. But meanwhile, our energy, if I'm talking about the atomic orbital, will have a different energy, then obviously there will be kind of partiality. So therefore there can be a disturbance that would create the distortion in the geometry, or the geometry will be disturbed. But this doesn't happen when the hybrid orbitals are being formed. So every kind of orbitals that are being formed because of the hybridization, they have the same energy, and that is playing a very vital role to understand that why the CH4 has a stable structure, why H2, even though having a not it is not a linear linear shape molecule, but still it is very much stable, and that is NH3 also, it is very much stable. So this is all been explained by the energy of the orbitals, and here in this case I have discussed about the energy also. So and talking about the next one, that is they only, obviously I have discussed this earlier only, that is the mixing of orbitals will take place in such a manner that the atomic orbitals that are mixing, they should have at least the same energy, and that is how we could say that the 2p orbital cannot be combined with that of the 3p orbital, because the energy level is very much different, and that is all the energy of orbital that I was talking about. So this were it, and there are a few examples, as I said, that we are going to discuss in the future lecture, but for a while this is okay for it. And the last one, and that is very much important, because this is the core part, that why orientation or why that is hybridization takes place, and let's talk about that also. And it says that the essential conditions of the hybridization, and those are very important. Starting with the first one, that is the atomic orbitals of the same atom can participate in hybridization. Obviously we have discussed about in the example like that of BeCl2. So the atomic orbitals like 2s and 2p, which are of the beryllium, they are combining with each other so as to form a hybrid orbitals, and that is the one responsible for the formation of bond with that of the Cl atom, which is a different atom, and that is how the bond takes place. The next point is only the atomic orbital and not the electron undergo hybridization. Yes, because electrons they can be shifted from from lower energy level to higher energy level, but they are not being compromised. The only thing that are being rearranged is basically the orbitals, and those only the atomic orbitals are the one that undergo hybridization, and electron doesn't undergo hybridization. It is only the one which is basically shifting its position from an orbital to another orbital, and that is what I was talking about. And this were these essential conditions of hybridization. And talking about the last one of it, that is the atomic orbital participating in hybridization should have the same energy level. So obviously all the energy, as I discussed earlier also, that is s orbital and p orbital of the beryllium, they will have the same energy, and that's the reason they are being making a hybrid orbitals, and that's it. So this were the most important thing of the that is hybridization concept and the steps that were involved in formation of the hybridization or hybrid atomic orbitals that I was talking about. So I hope you have understood this video very clearly, and I hope you'll share this video with your friends, and don't forget to subscribe to my channel. Thank you so much.